Scaling reinforcement learning is the primary mechanism for developing complex reasoning pathways in modern large language models today. This chart shows the latency breakdown of a standard RL training pipeline. The rollout phase, where the model generates its reasoning trajectories, dominates the timeline, consuming up to 70% of the total compute cycle. This delay is a requirement of algorithms like PPO and Reinforce++. Because these methods are strictly on policy, they require synchronous updates to function correctly. The model cannot update its policy gradients until every individual response in a batch has finished generating. However, autoregressive generation produces highly variable output lengths. In a single batch, one response might require 300 tokens, while another stretches to 16,000. When these factors collide, the hardware sits idle. The GPUs must wait for the single longest sequence in a batch to finish before they can move to the next step, creating this massive red block of empty space called a compute bubble. On enterprise clusters, this waste is quantifiable. Standard RL setups often operate with a 74% bubble ratio, leaving 3/4 of the hardware's potential performance unutilized. These synchronization deadlocks and routing inefficiencies create a hard ceiling for model scaling, limiting the reasoning capabilities we can achieve with current hardware. For standard inference, the industry typically solves GPU idle time through a technique called continuous batching. Continuous batching maintains hardware saturation by injecting new prompts into the queue the moment a previous response is completed. However, this optimization fails in reinforcement learning environments because the model weights are constantly changing. Policy updates alter the model during the rollout. If we use continuous batching, the older data in the queue becomes off policy by the time it is processed, which corrupts the trained data. This chart shows the PPO objective equation. It relies on an important sampling ratio to compare new and old policies. When off-policy data enters the gradient calculation, this ratio breaks, leading to unstable training. SortedRL was developed as a co-designed infrastructure to address this deadlock without compromising the underlying mathematics. The SortedRL architecture introduces two specific components, a length-aware controller for routing and a stateful rollout buffer to manage the data flow before it reaches the trainer. Eliminating the compute bubble requires a system that can surgically control when generations are interrupted while maintaining strict mathematical consistency. The length-aware controller manages the rollout through a strategy called oversubscription. The controller feeds the rollout engine more prompts than the queue capacity allows, ensuring the GPU always has a full workload to maximize batch saturation. To maintain order, the system applies early termination based on batching thresholds. Once a set of responses with similar lengths are finished, the system halts the remaining generations and forces an immediate policy update. This simulation shows the result. Aggressive oversubscription and early termination cause the system to organically batch responses of identical lengths together, snapping them into unified blocks and eliminating the idle gaps. This process creates a new problem. It forcefully interrupts long trajectories before they can finish. Discarding these interrupted sequences would bias the training toward short, simple responses, preventing the model from learning the logic required for complex problems. High throughput is only effective if the system can preserve the data integrity of these long-form reasoning steps. The stateful rollout buffer serves as the bridge between hardware-level interruptions and algorithmic stability. In its fully on-policy mode, the buffer scavenges unfinished prompts to ensure they are eventually processed, but it discards any partial text. The more efficient partial mode allows the buffer to cache the unfinished text trajectories directly. The buffer caches raw text segments on the left, paired with exact generation log probabilities on the right. Upon resuming, the system concatenates these cached probabilities with new ones. This stored data acts as the pi theta old variable, balancing the PPO equation despite the interruption. This architecture decouples the rollout batch size from the update batch size without destabilizing the training policy. By caching state rather than discarding it, SortedRL achieves the throughput of continuous batching while honoring the mathematical requirements of on-policy RL. The throughput gains are significant. Baseline systems process 3,987 tokens per second, while SortedRL in partial mode reaches 5,559. This efficiency translates to a near total reduction in hardware waste. The bubble ratio drops from 74% to just 3.37. On the AIME 24 benchmark, this microcurriculum yielded an 18.4% performance leap over the baseline with identical data. In the modern era of large-scale RLHF, systems-level pipeline routing directly dictates the true algorithmic capability of the model. For more on these systems, visit the Learn by Doing with Stephen YouTube channel and find the Stephen Data Talk podcast on YouTube Music and Spotify.